this is my slide that we'll be talking about. So as a software is a SIMCAT. So SIMCAT stands for Spectrum Engineering Advanced Monte Carlo Answers Tool. So this software is developed by the Europe Communication Office. So the software is basically used to predict the interference between two wireless communication systems, and the software has been used widely in academic areas such as our university, and we will see later in other also publication, and also used by the regulators such as the Malaysian Communication Multimedia Commission. Now I've been working since 2009, and we're doing research for the MCMC here based on this software. So basically the outlines, we have three outlines: the introduction, also the rules of coexistence, also and SIMCAT information. So we start introduction to SIMCAT. So as we can see here, that because of the increasing demand of the wireless communication systems such as mobiles, RFID, ultra-wideband, WiMAX, etc., and these new systems need spectrum allocation. Since the spectrum is a limited resource in each country and cannot be reused by other regulators, meaning that once the spectrum is used for a particular service, it cannot be reused by another service. So there's a problem that we don't have another new spectrum allocations for new systems, and so the regulatory and technological thing have to come in order to make to let this system use the existing band. And also, as we know, that the spectrum have economic benefit, and each country which have a good spectrum allocation and give it to good operators that will benefit both the country and the customer and the business. So from here we know why we need to share the spectrum. So because we don't have any more spectrum, that means limited resource, so we need to know a way of sharing it, meaning that when we put a new system, what are the method and ways it needs in order to coexist with other systems, so such as, do we need a guard band, do we need a separation distance, and also when, like for example, a new country deploy a system, how will it affect the neighboring country. For instance, now when we have in Malaysia and Singapore, they want to do the digital video broadcast, we have a problem from Indonesia that they're still using the analog broadcasting, so their systems is interfering the new systems. So we need to do, when we have a spectrum, we need to identify what are the sharing rules that we need. So what is SIMCAT? So basically SIMCAT uses Monte Carlo method. Monte Carlo method is a statistical tool that's being used when you have a large number of parameters, and for instance in finance and also telecom, when you have the one base station and hundreds of mobile stations, how we can predict what is the situation in each scenario. So we use a Monte Carlo. So the aim of SIMCAT is basically, at the end of the day, it will assess the interference level and based on the probability of interference. And the software has been developed by Europe, the European Conference of Post and Telecommunication Administrator, and it has been released since 2000. So it has been used widely by ITU studies such as ITU 2028 or something like that, also UK Ofcom, and in the research perspective can be seen many papers have been published in IEEE or Springer. And you can find out the latest publication. You can just get to Google Scholar and type SIMCAT, so you can see that what are the latest publications using it. So basically the purpose of SIMCAT is to model the systems, any system. For example, you have a generic system such as terrestrial or satellite or mobile. It can evaluate what's the effect of the transmitter and receiver mask, and from the transmitter and receiver, we know the unwanted emissions, meaning that the leakage emissions from the transmitter, and also the blocking and sensitivity. So these three we'll be talking more lately. So as a tool, what to do exactly is to quantify the probability of interference, and also to consider the spatial and temporal distribution of received signal, meaning that such as mobile. When you're a mobile user, you're a random, your place is random, so each position you have a different signal level and you have a different path loss from the so basically SimCAD can tackle such challenge, and it can model any systems, meaning that it can model terrestrial, it can model satellite, it can model fixed systems. So what are the system basically? Just like with a mobile, so you have a fixed transmitter or receiver and a mobile user with the random locations. You have a broadcasting where you have a fixed base station and also fixed receiver but at a distance or between 2 points, such as the point-to-point of systems, such as the backhauls and from city to city transmission. So what are the coexistence rules? Basically, we have three. So what is the methodology? What is the sharing scenario? And the system and simulation parameters, and finally how we quantify the interference. So let's start with the sharing scenario. So basically we have two scenarios. You have a code channel and adjacent channel interference. The code channel, for example, we have when you have the LTE Advanced, which is the 4 point something generation, because the LTE itself they name it as a 4G, so it's LTE Advanced, when it will be using the same frequency as the digital video broadcasting. So you have a code channel, so for the same frequency. And in order to mitigate the interference, we need a physical separation. This scenario usually is tackled by the country administration to handle such scenario. The most popular interference is the adjacent channel interference scenario, when you have two systems operate separated by a frequency domain. So when you have the same tower, this and this, so they're called co-sited. And this guard band is usually set by the regulator as how much frequency you need so that you operate your own system. So when we come to the sharing methodology, we have usually two methods: the minimum coupling loss and the multi-coupling. The minimum coupling loss usually tackles the situation of the worst case scenario, meaning that where you have only two fixed positions, but this one will not give you the real value and the real situation of the interference. Whereas when you have multi-color, you can know that you can random up to 20,000 snapshots. So the more snapshot you have, so the more accurate your probability of interference. So we have in the mirror coupling loss, so here we describe it, when you have your own transmitter and this is the receiver at the edge of the coverage, and you have a interferer. So we can know how much should be separation distance for that particular scenario. But this one is not optimal because your interferer may move or may be more than that interferer. So Monte Carlo comes into pictures in order to solve such problem. So you have the coverage here, you have your own receiver victim. So you may have a lot of interferer around you, but some of them are active, some of them are inactive. So we use the active interferer, and for each snapshot we calculate what is the distance for that and what is the received signal for that particular snapshot, then T0, T1, T, and so on and so forth. So we have the spectrum used in optimal way. So from that we can predict exactly what is the interference situation. So then we talk about the simulations parameters. So for the interferer, which is transmitter, we need to know the spectrum mask. We will talk about that. And from the victim receiver, you need to know what is your interference criteria, what's the receiver filter, what is your environment, and finally what's your propagation model. So propagation model is a mathematical representation of the channel that you're transmitting and receiving in. We will talk about this later. So these are the main elements. You have your own wanted transmitter, and this is the victim receiver, so it's receiving the desired received signal strength. And when interference introduced, which have its own system too, so it's causing the interferer receiver receive signal strength. So the receiver is receiving two signals at the same time. So these are the parameters. You have the radius simulation here. So this is the receiver. You have interferer. So the interferer have its own coverage and also the They want to have its own coverage, and this is from this perspective, from this particular receiver, we do the whole calculation. So this is an example of interference when we have the LTE came in Europe, and they have managed to they have calculated to use 1 megahertz as a guard band, but when it have turned on, many digital video broadcasting receiver lost signal due to that guard band. It was not sufficient enough to mitigate the interference. So this is how we model the interference. We insert the frequency, the power, what's most important, the spectrum mask, the height, and the gain. So for spectrum mask, basically, in an ideal scenario, yes, you can transmit everything in your bandwidth and nothing out of that. But because of the non-linearity of the electrical components, you may have harmonics and unwanted emissions being transmitted to the adjacent channel, which causes the adjacent channel interference. So the manufacturer or regulator need to identify what are the breaking points for that adjacent band so that we do the calculation to predict the interference. So this is how we model the spectrum mask and SIMCAT. So when you have your broadcasting, for instance, is receiving this in this band, so it receives everything here and supposed to be nothing here, and you have your own. There you have the mobile, which is transmitting an adjacent channel. So the mobile mask, spectrum mask, will fall into the receiver bandwidth, and the receiver bandwidth will receive the unwanted emission. So this is one part of interference. On the other side, from receiver perspective, also we put the receiver, transmitter, noise floor, bandwidth, whatever. What's more important here is the receiver blocking and what is the interference criteria. So the same for the receiver, it have to receive everything here and nothing here, but usually we do receive something from here, and this level is what we call the rejection of the receiver, is how good it can block the adjacent channel interference. So when you have your interferer, which is transmitting here, it will have to manage to block it to this level in order to maintain reception. So at the end, the interference is composed of unwanted emission and blocking. So this is the mask of the interferer, which falls within the reception bandwidth, and also the mask of the receiver would have to block the interferer carrier to this level in order not to have interference. If it cannot, then you have a interference due to the blocking. So this is the mathematical model of the total interference, which shows that when you have this transmitter system and receiver, so the transmitter is transmitting here, so the receiver is receiving some part of that, and also the receiver is receiving some of the leakage. So this is the total interference. So the total interference, which we call the adjacent channel interference ratio, is composed of the adjacent channel leakage ratio, which is the leakage from the unwanted emission, and the adjacent channel selectivity, how good your channel can select its own signal and reject the adjacent interference. And for the propagation model, so it depends on what system you're using. For example, if you're broadcasting, use the RTM model. If you're using the mobile, use the HATA. And each of these have own specification, the range of frequency and the distance also. So we have also short range devices, or we have spherical diffraction, or you can use the very general one, which is the free space loss, which is a very ideal case. So finally, we come to the quantifying of interference. So as we mentioned that for a particular receiver, it receives the wanted signal, and sometimes there are interferer. So the receiver listens everything, so it receives the C and the I, and the C over I, signal to noise interference ratio. So when there's no interference scenario, we have our own carrier, and we have the noise level, and we have the minimum acceptable wanted signal, which they call it the sensitivity. So from that, we know how much should be always the margin from this value to this value, which is done by the manufacturer, and the noise should be always with also this certain margin. For example, in digital broadcasting, the N over I should be always minus 6 dB, means that the I should be lower than the noise with 6 dB. If it's higher, then you have interference. So this is with interference. So when the interference get higher, it will make a new level which names N plus I, the noise plus interference ratio. And also for that, it will give the signal to noise interference ratio. Also, this is given by the manufacturers. So what is the maximum acceptable interference level for this particular? If you have higher than that, then your receiver is having interference problem. So this is what SimCAT uses to predict the interference, and this is the mathematical equations inside SimCAT that how they can find all these parameters. So this is how it shows the Monte Carlo goes. So when you have your victim, your interferer, so we do the calculation, the distance, the power transmit, whatever. So we have the first, for the snapshot, we have the first value for the DRSS. And for the interferer, you have your interferer signal, your wanted receiver, your interferer, interferer transmitter, and the wanted receiver. So from that, we find what is the interference, and we have the first snapshot for the interferer. And so on and so forth. For every snapshot, we have the second value of interference. And at the end, we may have something like that for the DRSS and IRSS. And we can average out to know what's the mean signal, interference signal, and desired signal. So how we quantify the interference from that? Well, we have our own target CRI. We know how much the margin. If this was lower, if you receive a lower value, that means we have interference. So if it was higher than the margin, so this is a good event. So from this we average out, we can know what's the probability of interference for that sharing scenario. So finally, SimCAT can be downloaded freely from the Europe Communication Office. You can also communicate with them, and you can ask questions, and they will respond immediately. And what's more beautiful in that, they provide what they have done as studies. So you can, for example, if you're using the digital video broadcasting or the third generation mobile UMTS, you can see what studies they have done in SimCAT and what are the criteria that they use to identify the interference. So there's a full detailed study in each. So SimCAT is not simply just a black box. No, it's an open source box. You can contribute, you can also program it, and each button they can show you what's the mathematical representation for that. That's all for my presentation. Thank you for listening.